Welcome to Chapter 5, Discrete Probability Distributions. This presentation is going to be broken up into two parts. First, we're going to cover the concepts of discrete probability distributions. And then in a second presentation, we're going to cover the binomial distribution, which is just a special case of discrete probability distributions. A random variable is a variable that's associated with probability values. A variable is just an entity that can take on different values, but the different values, or the range of values if it's continuous, is associated with probabilities. We're going to deal with the discrete case in this presentation. When we get into Chapter 6, we're going to deal with the continuous case, which is the normal. We're going to cover the concept of mathematical expectation. The expected value of a random variable is commonly referred to as the mean. We use the Greek letter mu, just like we did for the mean of a population. We're going to use that same symbol for the mean, or the expected value of a random variable. There's also the concept of variance. When you look at the difference between the value and the mean, when you look at that deviation and you square it and you come up with the expected value of that, then you found the variance. And just like as it was in Chapter 3, when you take the square root of the variance, you'll have the standard deviation. But in the next presentation, I'll cover the binomial probability distribution, which is just a special case. It's a special type of discrete probability distribution. Now, a random variable is going to have values which are numbers. It's describing the outcome of an experiment. When you have a discrete random variable, you're talking about values that ordinarily are integers. You're not going to have a variable with a value of 1.89234 or something like that. That's a continuous case. Now, you can have a finite number of values, or you can have an infinite sequence. An example of something with an infinite sequence would be like the number of customers that come into a store. You might have 0, you might have 1, but there's not really any limit on the number of possible customers. After a certain point, though, the probability is going to be 0 in a practical sense. But the continuous case, you can assume any value that's in an interval. You can also have sets of intervals, different collection of intervals. Now, this example for JSL appliances is for a discrete random variable with a finite number of values. X is the random variable, and we're saying that that represents the number of TVs sold per day. There are 5 values. That's a finite number. There may be 0, there may be 1, 2, 3, or 4, but it's not possible for some reason to sell more than 4 in a day. Could be an inventory situation. It could be that they're basing the probability distribution off of historical information and they've never sold more than 4 in a day. Now, this example is a fairly common example. It's still associated with the JSL appliances. X is the number of customers arriving in a day, but there's not really any upper limit on that. You could have 50 customers. You could have 500 customers. It's probably not very likely that you'd have 1,000 customers, but theoretically that's possible. We're not going to cover the Poisson distribution, which is ordinarily a random variable like this, what it would follow. But you can have infinite sequences of possible values for a random variable. Now, these are examples of different random variables. The number of dependents that's reported on a tax return could be 0, could be 1, could be 2. But you're not going to come up with 3.874 as a number of dependents, so this is discrete. But the distance from the home to the store, it could be 1 mile, it could be 2 miles, could be 1.38756 miles. But you can measure it finer and finer and finer, so that would be a continuous type of random variable. Now you could assign a number to the different states as to whether or not you own a dog or a cat. These are somewhat arbitrary assignments. You say, well, it's 1 if you own no pet. You could also say, well, it's 0. This one says 2 if you own dogs, 3 if you own cats, 4 if you own both. But you only have discrete values, a certain finite number that's possible. So this is a finite, discrete, random variable. Now the probability distribution, these are the probabilities that are associated with different values of the random variable. Now you can show these as a table, you can show these as a graph, but you can also calculate them through a formula. Now the next slide shows the situation for the appliance store where there's a finite number and it shows it as a table, and then it follows that with a graph. The formula aspect of it we're going to cover when we get to the binomial, which would be the next presentation after this one. Now the data that we're using to come up with the probability values was based upon sales over 200 days. On 80 of those 200 days, there were no televisions sold. On 50 of those 200 days, there was 1 television sold. So the probability that you're going to sell 1 TV is 50 divided by 200, which is 0.25. But it's more likely that you're not going to sell any televisions. There's a 40% chance, which is calculated as 80 divided by 200. But you can have a relative frequency distribution, and it's really the same thing as the probability distribution. But X represents the number of TVs sold. Now based on this data, what would be the average number of televisions sold? You could calculate the weighted average. You could take 0 times 80, you could take 1 times 50, 2 times 40, add up all the products, and then divide it by the sum of the weights, divide it by the 200, and you can come up with the average, which that's also referred to as the expected number. Now you can do the same thing with the probability values. You multiply the value of the random variable times the probability for that value. And when you take all those products and then add up all those products, that's the expected value. But it's also referred to as the mean. Now on the previous slide, the probability values were represented as a table. On this slide, they're represented as a graph. The line that's positioned at 0 goes up to 0.4. Probability for a value of 0 is 0.4. At 1, it goes up to 0.25. The probability for a value of 1 that they were going to sell 1 television was 0.25. But this is a graphical representation for that random variable. Now this slide shows the formula for the expected value of the random variable. The symbol that we use for that is the Greek letter mu. But you take the sum of the products, you multiply the value of the variable times the probability of that value. The f of x is the probability function. But you can use that function, if you have a formula for it, to calculate those probabilities. But all it is just a weighted average, and what you're using as the weights are the probabilities. Now it's always going to be true that when you add up the probabilities, they're going to add up to 1. So when you take the sum of the products and then you divide it by the sum of the weights, you're going to be dividing it by 1. And so you're going to end up with the mean. Now you need to notice that the expected value, it doesn't necessarily have to be one of the values that the random variable can assume. You can have values like 0, 1, 2, 3, and 4, but when you take the average of those values, it doesn't necessarily have to be a 1 or a 2 or a 0 or a 3 or a 4. It can be somewhere in between those. Now the variance of a random variable is defined as the expected value of the squared deviation from the mean. Now I know that this formula really doesn't look like the formula for the variance of a population, but it's really the same thing. You assume that each value in the population is equally likely, so the formula for the probability would be 1 divided by the number of items in the population, which the symbol we use for that is capital N. So the f of x would be 1 divided by capital N. So you're taking the sum of the squares of the deviations from the mean and you're dividing it by capital N. And that's just the formula for the variance of a population. And the symbol that we use for that is sigma squared. But we're using that same concept for the variance of a probability distribution. When it's discrete, you use summation to come up with a value. But all it is just a weighted average of the squared deviations from the mean. Now we can get the standard deviation by just taking the square root of the variance. Now this slide illustrates the calculation of the expected value of the random variable. X was the number of TVs sold in a day. But you multiply 0 times the probability of 0 and you get 0. You multiply 1 times the probability of 1 and you get 0.25. You multiply 2 times the probability of 2 and we get 0.4. 3 times 0.05, 4 times 0.1, and when you sum all those products up, you get 1.2, and that's the average, which is the expected number of TVs sold in a day. Now there's not going to be any day where we sell 1.2 televisions. It's the average. Most days we're not going to sell any. On quite a few of the days we're going to sell 1. Sometimes we sell 2, sometimes we sell 3, sometimes we sell 4. But the average, if you look at many, many, many days, you expect that average to be about 1.2. Now similarly, you can calculate the variance of a random variable. Once again, X stands for the number of TVs sold per day. We could have 0, we could have 1, all the way down to 4. Now the mean turned out to be 1.2. So you calculate the deviations from the mean. 0 minus 1.2 is a negative 1.2. 1 minus 1.2 is a negative 0.2. 2 minus 1.2 is 0.8, and so on. But you take the deviations from the mean and you square them. The negative 1.2 squared is 1.44. The negative 0.2 squared is 0.04, and so on. But you can take those values, the difference between the value and the mean squared, and you multiply those times the probabilities. So we take the 1.44, which was the deviation squared for 0, and we multiply it times the probability for 0, which is the 0.4, and we get the 0.576. You take the 1 minus the 1.2 squared, which is the 0.04, and you multiply that times the probability for 1, which was 0.25, and you get the 0.01. But you multiply the deviation squared times the probability. You get all those products, and then you add them up. You get the sum of those products. And in this case, the variance works out to be 1.66. Now, if you want to get the standard deviation, just take the square root of the variance. The square root of 1.66 is approximately 1.2884. Now there's a function in Excel that's called the sum product, and it's really useful in calculating the mean and also the variance for a discrete random variable. you can put the values of the random variable in one column and then paired up in the same row, put the probabilities in a different column. So A2 has the value 0, B2 has the value 0.4. But we have the value of the random variable in one column and the corresponding probability in the same row in a different column. Then we can use the sum product function to multiply all the numbers together and sum them up. But it's just almost perfect for doing this sort of thing. So if you look down there in cell B8, equal, that's what you do for a function in Excel, sum product, left parenthesis, you give it the list of the values. So here the values are from A2 to A6, comma, give it the list where the probabilities are. Here the probabilities are from B2 to B6, but it will element-wise take the products. It will multiply the value in A2 times the value in B2. It will multiply the value in A3 times the value in B3, and so on. And then it will add up all those products, and whatever the sum is, that's the number that's going to be stored in B8. Now the formula that's in C is to calculate the squared deviations from the mean. The mean is stored in B8. So the formula that's in C2 says take the value of the random variable, which in A2 that's 0, subtract the value of the mean, figure out what that deviation is, and then raise it to the second power. You square it. Now those dollar signs that are on B8, that makes that an absolute reference. And if you do it that way, you can just copy that formula and paste it in the cells below it, and it will automatically populate them to do all those calculations very, very quickly. But those numbers, those are what you need to multiply times the probabilities and sum up the products to get the variance. And that's what the formula in B9 is doing. You're taking the sum product, you're taking the numbers, the squared deviations from the mean that are in column C, and element by element you're multiplying them times the probabilities. And when you take the sum of those products, you're going to get the variance. So the variance is going to be calculated and it'll be stored in B9. And then all you have to do is take the square root of the variance to get the standard deviation. And the SQRT function is the function in Excel for square roots. Now this slide shows the values that were calculated by those formulas in Excel. When you take the 0 times 0.4, the 1 times 0.25, the 2 times 0.2, the 3 times 0.05, and the 4 times 0.01, and take the sum of all those products, you get the 1.2. But it's a sum product function that you're using for that calculation. Now the value that's in B9 is also a sum product function to calculate that number, but you're taking the 0.4 times the 1.44. Now the 1.44 is being calculated as the difference between the 0 and the 1.2 that's in B8, and you're taking that difference and squaring it. But when you take the deviation squared, multiply it times the probability, and do that for every case, and add up those numbers, you get the variance. And the variance for this particular problem turned out to be 1.66. And then all you have to do to get the standard deviation is just take the square root of the variance. Now that concludes the discussion, just the basic elements about discrete probability distributions. We didn't really cover a case where we had a formula for coming up with the value for the probability, but we're going to do that in the next presentation when we cover the binomial. The binomial is just a special case of a discrete probability distribution. Now it turns out that all these calculations that you do to figure out the expected value, or the mean, to figure out what the variance is, standard deviation. Those are very, very easy to do if you have a binomial random variable. But we'll get into that in the next presentation.